my God, logarithms. Okay. So, as we already said, logarithms are the inverse of exponential functions. And there are some common logs that you'll see like on calculators. Elsewhere. You'll see these a lot. Actually, hang on. Before we get there, let's back up. So remember our exponential functions were a to the x. And if we write that as an equation, set it equal to some number b, it doesn't matter what numbers these are, then the inverse of that equation, if we take the inverse, that will be the log of a, base a, and then base a of b equals the exponent x. So in both the exponential and in the log, the base is the same. It's this a, whatever a is. And the exponent goes on the other side of the equation. Okay. Now, the base, I mean, any of these numbers, a, x, and b, they can be anything. But there are common logs that you'll see a lot that have specific bases. So like on your calculator, you'll see log, and then you could put in a number, it doesn't matter what, log of b, but it doesn't have a base there. It's just empty. What this is, it does have a base, it just doesn't show it. The base here is 10. So if you see a log and it doesn't have a base, it's 10. Assume it's 10, yeah, exactly. The other one is ln of b. Now here, you also don't have the base here, it doesn't show it. But here, whenever you see ln, that means log base e of b. And again, e is the natural number we talked about last time. It's like 2.71, and it continues on infinitely, just like pi does. Okay, so let's talk about what this actually looks like. We can compare it to the exponential function. So the exponential function, if you recall, it looks like this. This is like f of x equals a to the x with no transformations or anything like that. The log function looks like this. Okay. And so, again, if you recall, the domain and range.
Wait, so that top one is not, the bottom one's the log?
The green one is the log.
Okay.
Yeah, here, I'll write.
With the log of each other, where are they? Does log like only have to do with like a certain number of like?
Log is a specific function. And again, it's the inverse function of an exponential. So yeah, no, only the green one is the log, and it'd be log base A of, well, B, something like that. So for the exponent, remember,
So what is the top one equal? F of x equals
like a to the x. Yeah,
and the bottom one is log e.
yeah. Okay. And so for the exponent one, if we recall, the domain is, well, we look, it goes all the way to the left and it just keeps going. So it goes from negative infinity. And even though it does get really big, really fast, it still goes all the way right to positive infinity. So this is what we covered like last week. And then the range, if you recall, no matter what you put in the exponent, no matter what exponent, even if you put a negative number, remember, it just gets closer and closer to 0. So this never actually goes below 0 here. So the range is 0.
Is it a bracket? No, it's not.
No, because it never actually touches. Yeah, yeah. That's a good question, though.
0 to
Infinity, yeah. Okay. Now, I'm going to tell you this, and then we're gonna show why that it's the case. Whenever you have an inverse, the domain and range flip. So for log, it's going to be 0 to infinity for the domain, and negative infinity to infinity for the range. Here, I'll give you. We can see how it flips because if you look at the graph here, well, you can see that it approaches 0, but in the same way as it did horizontally here, it never actually approaches 0. So that's why the domain, the x values, start at 0, and then they, as you go further and further right, they just continue on, so it goes to infinity. Similarly, the range, well, it goes all the way down in the y and continues, and then it keeps going all the way up in the y as well, so that's why it's negative infinity to infinity. The other thing with inverses, you might recall this, is when you plot the two inverses, they are symmetric about the line y equals x.
I think I remember that,
Yeah. And it makes sense too, because like whenever one way to find an inverse is to just literally flip the y and the x. So you're just, anytime you see a y, you put an x in. Anytime you see an x, you put a y in, and then you solve for y again. So and I don't know, that it makes sense to me that it would be symmetric about that line. So that's the plot of logarithms. And there are a lot of rules. Did you get all that, by the way? Okay. There are a lot of rules for logarithms, like manipulating them. So let's go through those. So the first one is if you have log base A of B plus log base A of C, then you can combine those, you can condense that, and it becomes log base A of B times C. Now, important thing here is the bases Must be the same, yeah, exactly. If they're not the same, you can't do it.
Mm-hmm. Wait, do I have lunch after this?
Yes. Yes. I know, I'm hungry too. Okay. Then you will have log base A of B minus log base A of C. What do you think that is?
B minus, log A, B minus C. Or B divided by C.
Yes, there you go. Good. Okay. Excuse me. Okay. If you have log of A of B to the C power, this can be rewritten as C times log of A to the B, which is kind of weird, but basically the C just comes down and gets multiplied by that. And all of these, by the way, they can be done in either direction. So sometimes you'll get problems that'll tell you to either expand or contract the problems. So if you have a log of A of two functions, like B and C, multiplying, and it wants you to expand, you can, go in this direction and make it to where you have two log functions adding. But yeah. Okay. There's one, it's called the change of base. This is important because it allows you to plug in any log into a calculator. So let's say you have log of A to the B, normal. This is equal to log, we'll say 10. So again, since it's base 10, we don't actually write the base. So log B over log A. Now, it doesn't have to be log base 10. You can do any base here. It doesn't matter. But you'll want to do either base 10 or ln because those are the only two that are in your calculator generally. And the way to remember this rule is the higher number on top, lower number on bottom. And when I say higher and lower, I don't mean like larger and smaller. I mean like literally the B is higher up than the A. So that's the one that goes on top of the fraction. And yeah, this way, like if you have like, let's say log, example, log base 3 of, 10. Well, you normally couldn't enter this into your calculator, but you can use the change of base to turn it into log base 10. So you'd have log 10 of 10. Well. Don't write the base. Log 10 over log 3. And now you can enter that in your calculator. Okay.
Oh, so the one that is physically higher. Yeah, that makes more sense.
Physically higher. Yeah. Okay. The next is kind of like a result of logs and exponents being inverses of each other. But let's say we have log base A of A to the x, like that. That is simply x. In the same way, if we have A to the log base A of x, that is also x. And it's because what we're doing is we have the log function and we're plugging its inverse inside of it. And you might remember, do you remember composition functions? You might have seen it like this, or like f of g of x, like where you take one function and you plug it inside the other one.
So, yeah.
Okay, that's exactly what we're doing. And whenever you do that with inverses, they cancel each other out. And what I'm doing is I'm going through all the rules right now. Then we'll go through like specific examples of them. So we'll actually use them. And on your test, by the way, I'm going to pause this. All right, so let's see, what else is there? Oh, these aren't really rules, but special cases. So any log is a of 1 is equal to 0. It doesn't matter what the base is. And the reason why, well, we can see if we convert back to exponent. So what would this equation be in exponent form?
Exponential form?
In exponential form, yeah.
1, start off with 1, right?
Look at what I wrote at the beginning, or here, if you don't have it. So if it's
This one just log a. Yeah, it's the same. Your exponential function. I don't know.
so right here, see if we have log base a of b equals x, then that becomes base a. Remember the bases are the same. And then the other side of the equation becomes the exponent.
Yeah. So wait. It becomes. Doesn't it just become a?
Yes, a is the base. And so what's the exponent now?
The exponent is 1. 0.
0, yeah, 0. 0, and then on the other side of the equation?
What? I didn't know there was one.
So here you have ax equals b, or
Log a.
log ab equals x. So if we're converting it back here, the b goes to the other side of the equation. So the b here is 1, right? So that now goes on the other side here.
Okay.
We'll do some more examples, but any number to the 0 power is equal to 1, right?
Is that your notification? Is that the switch?
It is the switch, yes. But yeah, so this is the reason why this is true, is because any number to the 0 power is equal to 1. So that's why, yeah. Log base a of 0, and I'm writing a because it doesn't matter the base, does not exist. In fact, this cannot be negative. You can't put a negative number into the argument of a log function, because if we go back to the plot, sorry, I'll go back so you can write it. But if we go back to the plot, it never crosses the 0 line. So anything 0 and below does not exist in the function. And here, so I'll let you write that.
Like 1 or D and E?
D and E does not exist.
Oh,
Sorry.
okay. I was like, 1? That's a weird thing to write. it's like, is 0 negative? Well, it's not negative, it's positive.
It's not. No, 0 doesn't work either, but neither, because again, it never actually touches 0. It gets closer and closer to it, but it doesn't touch it. So that's why 0 doesn't work, and neither does any negative number. Yeah. Yeah. Okay, so these are the rules that we're going to use to manipulate these log functions. So, but first, let's just go back to converting some logs to exponential form and vice versa. So let's say we have 2 to the x equals 10. So what would this be in logarithmic form?
2x, logarithmic form would be log 2.
Good.
Log 2, 10.
Yes.
Yeah.
Good. And then what does it equal?
X.
Yes.
Right.
Awesome. Good job, man. Okay.
Huh.
All right. Let's do another one. Let's say 5 to the 2x equals 25. What would that be?
Log 5.
Good.
5 is 2x. Wait, is that right?
Log of 5 is correct. Log base 5.
No, it's to x. Or 25.
25, yeah. What the? Sorry. And then it equals
2x.
2x. Good. All right. Let's go in reverse.
Okay.
Let's do, I'm going to throw a curveball at you. ln of 12 equals x. So what would that be in exponential form?
Exponential form.
First of all, let me ask you this, actually.
12. Start off 12.
Not quite, no. So what is the base here? If I have ln, what is the base?
Isn't it 12? Or is it ln? Or is it x?
It's neither. No, there's, remember, like with logs, the base is the number that's down here.
Oh, yeah.
But with
So it's 10.
ln is a special one. If it was 10, it would just be written as log, and there'd be no number. But ln is the other one.
Yeah, no, but I didn't write down that.
Okay, okay. That one is base e.
Okay, no, I wrote that. I didn't know. Yeah, I wrote log e. Log e.
Okay. So yeah, that's the base. So then it would be e is our base. And then what becomes the exponent?
Will it become log e?
Not quite, no. Maybe it'll help if I rewrite it like this.
For e12?
If I rewrite this way, does that help at all? So again, the bases stay the same. We still have e as our base. And then we have to have some number up here as our exponent and then equal to some number. So what number goes in the exponent?
12.
Not quite. X, yeah. Okay, and then on the other side of the equation?
12.
Yes, yes, yeah, okay. Okay, let's do another one of those. Say log base 5, 2 equals x minus 1. Then log base 5, 2 equals x minus 1. We're converting that to exponent form. Okay. So what's the base in exponential form? Jesus Christ.
It's still log. I start off with what?
No, because we're switching it to this form here. So in the above example, we had log base
5.
e. Yes, yeah, 5. Yeah.
5 to x power.
Close, but it would just be the entire right side. It would just be x minus 1.
Oh, yeah, no. 5.
Again, I kind of threw a curveball at you, but and then what does that equal to?
2.
2. Yeah, good. All right, and so yeah, that's how we convert between logs and exponential forms. Now, sometimes we'll need to use the rules. The first question we want to ask is, what is the base here? What are the bases for these?
We'll like log.
What's the base of the log? So remember, the base, when I ask you that, what I'm talking about is this number. That is the base, the number at the bottom.
I guess it's...
So here we don't see a number for the base.
Yeah.
So what does that tell us?
It's E. Or no, it's not E. It's 10.
10. Yes, good. So it's base 10. And notice these are all log base 10 because none of them show one. So it means they all have to be. Which is good because we'll need to use that to use our rules. So what we want to do is solve this equation, and we can do that by combining these things using the rules that we have, and then so first one, we can use the second rule, this subtraction rule here. If we have two logs of the same base and they're subtracting, then it becomes log b over c. So here what that would be is log base 10. Here b is 6x, and c is 4 minus x. And that's still equal to log of 3. Right, yeah, because of the rule 2 that we wrote down. So if they're the same base and they're subtracted by each other, then it's B over C. You just divide them.
I just gotta let you know it's gonna smell rancid in here in about like 10 seconds. I'm sorry, I'm just pressed. It's the most.
So one thing I didn't say is if you have on either side of the equation, log A, let's say this is B equals log A of C. If on either side of the equation you have a log with the same base and only just like one log on either side, you can ignore the log functions and just look at the inside. So we're just going to ignore the logs entirely and just say B equals C. We can do the exact same thing with exponential functions. So if we have the same base, let's say a to the b equals a to the c, like that, with the same base on either side and only those functions, then we can do the exact same thing and just ignore the bases and just set the insides equal. So the reason why I say that is because here we have that exact situation. We have log base 10 of this thing inside equals log base 10 of 3. So we can just ignore the logs and set the insides equal. And now we just solve for x. So we'll multiply both sides by 4 minus x.
Yeah, I don't know how to oh, yeah. Okay.
So if we multiply both sides, we get it out of the denominator, and it becomes
12 minus 3x.
Yes. Yeah. Good.
And then that becomes 9x equals 12.
Mm-hmm.
And so that x equals 1 1/3.
Yeah. Good. 4/3. Yeah.
Ooh.
Good job. All right. So yeah, that's how we go about solving these types of problems. Let's do another one. Okay. So now this one, we only have one log function. But since the x is inside, we can't really solve for the x. We can't just like take it out of the function. So in order to solve for x, we first need to convert it into an exponential form. And then that'll, because in an exponential form, this will be outside of the function. So what will this be in exponential form? Mm-hmm. Yeah, good.
Start with 2, that equals 25.
25 and minus x squared. Yeah, yeah, exactly. It's whatever's on the inside. It's all equal to that. Good. All right. So yeah, 3 to the 2. That's just 9. It's equal to 25 minus x squared. So what do we do next?
We subtract
Yeah, well, so that's one thing. So the negatives will cancel, and we get square root x squared, or square root 16. But we can't forget, and I say we can't forget, but I did forget to mention this the other day, that whenever you take the square root, you have to remember that you could either have the plus or the minus. Now, so that'll become plus or minus 4, but we have to check it. So if we had plus x equals plus 4, when we plug that into our original equation, we have log base 3 of 25 minus 4 squared, so 16 equals 2. 25 minus 16, that's 9. That's okay. We can have that. That's valid. If it's x equals minus 4, that's log base 3 of 25, still minus 16, because minus 4 squared is still 16, positive 16. So that's also valid. So in this case, plus and minus 4 are both solutions. But sometimes you'll have a case where yeah, exactly, because the reason why is like whenever you plug one of them in, the inside of the log will become negative or 0. And remember, that doesn't exist. So that's why we have to check it. All right. So that's it. I will